Hello student, in previous lecture we have seen a squeeze theorem to check whether given sequence is convergent or not. Now today we are going to start one more method, the Alembert ratio test for convergence of sequence. Okay, so what this test said, if xn is a sequence of positive real number and if limit n tends to infinity, xn plus 1 divided by xn is equal to L exists, if this limit exists, and if L is less than 1, then sequence xn is convergent. The sequence xn is convergent and limit n tends to infinity, xn is equal to what? 0. So what this test said, if your sequence is a positive sequence, positive number sequence, real number sequence, and if limit n tends to infinity, xn plus 1 upon xn is equal to L, if this limit exists and your limit L is less than 1, then sequence xn is converges and converges to what? 0. So if we want to prove this, again we have seen one theorem. If our sequence is a given sequence is a positive sequence, then its limit is also positive. That is, if xn is greater than or equal to 0, if the xn is greater than or equal to 0 means what? Its limit, since xn is greater than or equal to 0 for every n, this implies our L is also greater than or equal to what? 0. So let R be any number such that let R be any number such that L is less than R is less than 1. Then for take epsilon is equal to R minus L, which is greater than 0. Now since this sequence is convergent, for this epsilon there exists a natural number k belongs to n, that is a natural number k such that xn plus 1 minus xn minus L is less than epsilon for every n is greater than or equal to k. For every n is greater than or equal to k. Now again all of you know that if x mod of x is less than a, implies this number is lie between minus a and plus a if your a is greater than 0. Now since epsilon is greater than 0, this number is less than epsilon and minus epsilon that is this lie between minus epsilon and plus epsilon. So what this implies, xn plus 1 divided by xn minus L is less than epsilon. So what this implies xn plus 1 divided by xn is less than epsilon. I am not writing here minus epsilon because we require just this term, that is xn plus 1, xn minus L is less than epsilon. Okay, I am writing here that is minus if mod of x is less than a, then minus a less than x less than a if our a is greater than 0. If a is greater than 0. So but what is epsilon plus L? If we take this L to this side, then xn plus 1 upon xn is less than epsilon plus L. But what is epsilon? Epsilon is what? R minus L. So if we put this R minus L, then xn plus 1 divided by xn is less than R plus L minus L. So this plus L minus L will get cancelled here, and this term is less than R. What this implies? Xn plus 1 is less than xn R. Similarly, if we apply the same logic, that is xn is less divided by xn minus 1, xn minus 1 divided by xn minus 2, we obtain this xn R is less than xn minus 1 R square. xn minus 1 r square. Then this is less than xn minus 2 r cube. Similarly, all these are less than sk is less than r raised to n minus k plus 1. Successively, all these terms are less than or equal to. So what this implies? Okay, what this implies? Xn plus 1 is less than sk. If we simplify this term, then it is r raised to n, r raised to minus k. That is r raised to n plus 1 minus minus plus k minus 1. Sorry, not k plus 1. N plus 1, because here r square, r cube. So it is what? K minus 1. N plus 1 divided by into r raised to minus k. This r raised to minus k can be written as r raised to minus k can be written as xn plus 1 is less than sk divided by r raised to k into r raised to n plus 1, r raised to n plus 1. Okay, now for every n is greater than or equal to k, for every n which is greater than or equal to k. Now if we write capital C is equal to, or C is equal to x raised to k, r raised to k, then 0 less than or equal to xn plus 1 less than or equal to c r raised to n plus 1. But what is here? For every n which is greater than or equal to k, for this term if we write the constant c, then xn plus, why this xn plus 1 is greater than 0, greater than or equal to 0? But because the given sequence is a sequence of positive real number. So x0 less than or equal to xn plus 1, this is less than c into r raised to n plus 1. If you take limit n tends to infinity, and by using squeeze, so if we apply a squeeze theorem, then this limit n tends to infinity. Since r 0 less than r less than 1, this implies limit n tends to infinity, r raised to n plus 1 is converges to what? 0. So 0 less than or equal to xn plus 1 less than or equal to 0. What this implies? This sequence is converges to what? Limit n tends to infinity, xn plus 1 is converges to what? 0. Okay. If this sequence is converges to 0, this sequence is converges to 0, you are by using squeeze theorem, this sequence is also converges to 0. But xn plus 1 is converges to 0 implies what? Xn is also converges to 0. Now, for example, show that xn is equal to n divided by 2 raised to n. This sequence converges to 0. Now this sequence is a sequence of positive real number. For every n, this is this sequence is a sequence of positive real number. Or you can check, put x is n equal to 1, then it is a positive n equal to 2. Each term is positive, therefore it is a sequence of positive real number. And if we apply the Alembert ratio test, then what is xn plus 1? Xn plus 1 is n plus 1 divided by 2 raised to n plus 1. Xn plus 1 divided by xn implies this divided by n divided by 2 raised to n. And therefore limit n tends to infinity, n plus 1 divided by 2 raised to n, and 2 raised to n plus 1 can be written as 2 raised to n into 2 multiplied by 2 raised to n divided by n. So this 2 raised to n will get cancelled here, and it is equal to limit n tends to infinity, take this 1 by 2 outside, take this 1 by 2 outside, take this 1 by 2 outside, it is n plus 1 divided by n. If we divide it by separately, then limit n tends to infinity, xn plus 1 divided by xn is equal to 1 by 2, limit n tends to infinity, 1 plus 1 upon n. But what is limit n tends to infinity 1 upon n? It is 0. Okay, so it is equal to, and 1 plus 0 is 1. So this limit, that is xn plus 1 upon xn, is converges to 1 by 2, which is what? Which is less than 1, and therefore limit by using the Alembert ratio test, limit n tends to infinity, xn is converges to 0. That is, this sequence is converges to 0. Why? Because this limit is equal to 1 by 2, which is less than 1, and therefore by using the Alembert ratio test, we can write this sequence is converges to 0. Take one more example. Show that limit n tends to infinity. Show that the sequence xn. Is equal to n factorial divided by n raised to n converges to 0. So now again, if we apply the Alembert ratio test, when the Alembert ratio test is applicable, if your sequence contains factorial term or raised to n term, then you can apply the Alembert ratio test. So consider limit n tends to infinity, xn plus 1 divided by xn, that is equal to limit n tends to infinity, n plus 1 factorial divided by n plus 1 raised to n plus 1, and again this divided by n factorial by n raised to n. So we can write this as n raised to n divided by n factorial. So if you simplify this, it is equal to limit n tends to infinity, this n plus 1 factorial can be written as n plus 1 into n factorial into n raised to n divided by this n plus 1 raised to n plus 1 can be written as n plus 1 raised to n into n plus 1 into n factorial. So here n factorial will get cancelled here, n plus 1 will get cancelled here. So what is left here? Limit n tends to infinity, n raised to n divided by n plus 1 raised to n. Okay, so this can be written as limit n tends to infinity, n divided by n plus 1 raised to n. This can be written as limit n tends to infinity, 1 divided by 1 plus 1 upon n raised to n. Okay, this n written as we can write this n as divided by n. So 1 divided by 1 plus 1 upon n, but all of you know that this limit is what? The value of this limit is e. So this sequence is converges to 1 upon e, which is less than 1 upon e, which is less than 1, and therefore by the Alembert ratio test, this sequence is converges to what? 0. So we are going to stop here for today.